Welcome back to the Deep Dive, where we crack open the most fascinating research and bring you the insights you need to stay ahead in our rapidly evolving digital world. Today, we're plunging into a realm where digital secrets are vulnerable, not through mathematical flaws, but through physical whispers, and how groundbreaking new technology is building, well, hopefully, an impenetrable shield. Imagine, if you will, a secure vault, locked tight, with an incredibly complex mechanism. The designers assure you the mathematical permutations for the combination are virtually infinite. It's theoretically unbreakable. But someone isn't trying to guess the code, nor are they trying to force the door open. Instead, they're listening with incredible precision. They're listening to the subtle sounds the tumblers make as they fall into place, the minuscule power fluctuations when the gears shift, the tiny vibrations that ripple through the metal as the mechanism performs its intricate work. Every subtle physical hint, every whisper of energy is being meticulously gathered and analyzed to deduce the secret combination. Now let's pull that fascinating, almost cinematic image directly into our digital reality. Because at its core, this is precisely what a side-channel attack looks like in the world of microchips and data processing. It's an insidious form of digital espionage. The core problem we're confronting today is a fundamental vulnerability. Even mathematically secure cryptographic implementations, think of something as robust as the Advanced Encryption Standard AES-256, can inadvertently leak secret information. This isn't because the underlying math is broken or flawed. It's because the physical way that math is implemented in hardware gives off telltale signs, like those subtle clicks and vibrations from our vault. These side channels are things like minute changes in power consumption as a chip processes data, faint electromagnetic emanations that are essentially tiny radio signals whispering about the computation, or even slight timing differences in how long an operation takes depending on the specific data it's handling. And here's where the threat has truly escalated and taken on a new, terrifying dimension. Machine learning, or ML, and particularly deep neural networks, have supercharged these side-channel attacks beyond anything we've seen before. What used to be a difficult, incredibly resource-intensive process, demanding millions of data points and specialized human expertise, can now be done with alarming efficiency and automation. We're talking about recovering secret cryptographic keys with just a handful of power traces, those detailed recordings of power consumption. This isn't just an abstract academic concern. It's a huge, immediate, and pervasive threat to the small, ubiquitous devices all around us. Your IoT sensors that monitor your home, the smart cards in your wallet that handle your banking, the embedded systems powering everything from your car key to life-saving medical devices. These devices often operate in untrusted environments and need to perform their cryptographic functions securely for only brief periods. They simply don't have the luxury of performing millions of cryptographic operations before an attacker can gather enough traces to compromise them. So the natural, urgent question becomes, what do we do about it? How do we build a truly robust defense against an adversary powered by increasingly intelligent AI? And this is precisely where the groundbreaking research we're exploring today comes into play. The team behind this research had to fundamentally rethink the problem. Instead of simply trying to mask or attenuate the signal, they asked, what if we could make that sound from our digital vault so inherently unpredictable, so dynamically chaotic, that even the most sophisticated AI couldn't possibly make sense of it? What if we could introduce physical time variance directly into the hardware's operation? Today, we're going to tease apart some truly groundbreaking research that introduces a lightweight, synthesizable technique that deliberately introduces this physical time variance to disrupt these incredibly potent ML-based attacks. The technique we're focusing on is called the switched capacitor-based time-varying transfer function, or SCTDTF.
Right. That's a powerful claim, a fundamental shift in defense. Could you perhaps elaborate on why this concept of time variance is uniquely effective against the relentless pattern recognition of deep neural network-based machine learning side-channel analysis, especially those utilizing convolutional neural networks, or CNNs? What makes their pattern recognition so formidable that older signal attenuation methods simply couldn't touch them?
That's a really good question,
Yeah.
because it's not just about making the signal quieter, right?
Exactly. CNNs are exceptional at learning hierarchical features, and they're often designed to be translation invariant. This means if a pattern is present, even if it shifts slightly in time within a signal, or in the case of a side-channel attack, if the power consumption peak for a specific operation consistently appears at time d, but then is deterministically shifted to 8 plus delta, the CNN can often still recognize it.
Ah, okay, so the simple shifts weren't enough.
Pretty much. Older countermeasures that simply shifted patterns deterministically or attenuated signals were essentially providing distorted but still recognizable fingerprints to these highly adaptive AI models.
Fine.
SCTVTF's true insight is that it doesn't just distort. It fundamentally shuffles and randomizes the temporal relationship of information. It makes the fingerprints so utterly inconsistent that the CNN can't find any stable feature to learn from.
So it's not just a shift, it's like
Yeah.
shredding the timeline.
You could say that. It's a complete temporal disintegration of the attack surface, turning consistent patterns into pure noise for the AI.
That distinction is incredibly important. So our mission today is to dive deep into this fascinating paper from Arkisman Ghosh, Debayan Das, Santosh Ghosh, and Shreya Sen. We'll explore how their SCTVTF system protects digital secrets by making the physical world inherently unpredictable. You'll learn what makes ML-based attacks so potent, why previous defenses struggled, and how this new approach offers a dramatic leap in security for the devices all around us. When we talk about dramatic, what kind of order of magnitude are we discussing here, and why is it so much more effective than what came before?
Well, to put it into perspective, this isn't just an incremental step, it's a monumental leap forward. We're talking about outperforming existing methods by over 5x in terms of the number of traces needed to train an attacking neural network.
5 times. That's significant.
And by a truly staggering 100,000x compared to an unprotected system.
Wow, okay, 100,000 times, that's
Yeah.
huge.
It is, and what makes this particularly fascinating is that it directly addresses the Achilles heel of previous countermeasures when faced with the relentless pattern recognition capabilities of deep neural networks, especially those utilizing CNNs where older methods simply fell short. It's a fundamental shift in how we approach hardware security.
Okay, let's start by truly understanding the threat we're up against, because it's been evolving at an incredible pace, far beyond what early researchers might have imagined. When we talk about side-channel attacks, or SCAs, we're really elaborating on that vault analogy. It's not about breaking the mathematical encryption algorithm itself, which is designed to be incredibly complex and secure. Instead, it's about exploiting the physical characteristics of how that algorithm is implemented in hardware. Think of it as a subtle form of eavesdropping, where the device itself inadvertently broadcasts clues about the sensitive data it's processing. We've identified several primary examples of these physical side channels, each offering a distinct pathway for an attacker to glean secret information. First, and perhaps the most widely studied, are power traces. Consider the tiny power draw of a microchip as it performs calculations. Different operations, or the processing of different data, say, manipulating a byte with a lot of 1 bits versus one with a lot of 0 bits, can cause minute but distinct variations in power consumption. These aren't just random fluctuations. They often correlate directly with the data being processed. For example, the number of 1 bits in a byte, known as the Hamming weight, or even the subtle transitions of individual logic gates as they switch from high to low.
Right. It's critical to understand that these power consumption variations, though small, are not arbitrary. They are a direct physical manifestation of the internal computations.
Exactly, and power is just one channel.
Precisely. Secondly, we have electromagnetic EM emanations. Every electronic component generates tiny radio signals as it operates, much like a miniature radio transmitter. These EM emanations are like faint whispers of computation, subtle radio waves that, with the right equipment, specialized antennas, and spectrum analyzers, can be picked up from a short distance and decoded. These emanations can reveal similar information to power traces, sometimes even more granular details about specific internal registers or data lines.
Okay, so power and EM signals.
Yeah.
What else?
Thirdly, there's timing information. Even mathematically identical operations can take slightly different amounts of time to complete, depending on the specific data being processed, or even due to internal memory access patterns. For instance, comparing a secret key to an input might take slightly longer if there's a mismatch at a certain bit position. These minute timing variations, sometimes only a few clock cycles different, if observed over many operations, can reveal critical information about the secret key.
Like a subtle, almost imperceptible hesitation.
Exactly. Imagine a subtle hesitation in the vault mechanism that only occurs when a specific digit is turned. All these channels, whether power, EM, or timing, offer an attacker a window into the otherwise mathematically secure operations inside the chip.
And this is exactly where the vulnerability lies. These aren't design flaws in the cryptographic algorithms themselves.
Which are mathematically robust, rigorously peer-reviewed, and often certified by national standards bodies.
Right. The problem arises from their physical implementation in hardware, which, by its very nature, leaks these subtle, measurable side channels into the environment.
It's a fundamental challenge of building secure systems in the real world. The abstract mathematical security is compromised by the concrete physics of computation.
And here's where it gets really interesting. Machine learning, particularly deep neural networks, has completely changed the game for side-channel attacks. Before ML, attackers needed a deep understanding of the specific hardware, often using complex statistical methods like correlation power analysis or CPA, and a massive amount of data to manually identify correlations.
It was painstaking work.
Definitely. ML automated and amplified this process, making it far more efficient, far more potent, and capable of finding patterns that human analysts or traditional statistical tools simply couldn't discern in noisy data. Let's break down how a DNN-based SCA typically works, which usually involves two distinct phases that make these attacks so devastating. The first is the training or profiling phase. In this stage, an attacker has access to a device similar to the target, or perhaps even the target device itself, in a controlled environment. They feed a known input, say a specific plaintext message, to the device and record its power traces as it encrypts that data using a known secret key.
They basically build a profile of the device's leakage.
Exactly. They repeat this process many, many times across various inputs and known key values. This allows a deep neural network model to learn the incredibly subtle, often nonlinear correlations between the cryptographic operations, specifically the intermediate values derived from the secret key, like the output of an SBox operation, and the leaked physical data. You could think of it as painstakingly fingerprinting every single possible sound a safe makes for every tiny movement, mapping each sound, even in a sea of background noise, to a specific internal state or a specific part of the secret combination.
The DNN essentially builds a highly detailed predictive model of the device's leakage behavior.
Once that DNN model is meticulously trained and has effectively learned these correlations, the attacker moves to the attack phase. Now, they take the trained DNN model, which is essentially a highly optimized prediction engine, and apply it to an unknown target device. They feed an unknown plaintext into this device, record its power traces, and then the pre-trained DNN model analyzes these new unknown traces. Based on what it learned in the training phase, the DNN can then predict the secret key with astonishingly high accuracy.
Even if it has never seen that specific key before.
Right, it's like presenting the trained safecracker with the sound of a new, unknown safe operation, and they can instantly tell you the combination.
This raises an important question. Why is ML so uniquely effective here? Because it excels at identifying incredibly subtle, complex, nonlinear patterns in noisy side-channel data that humans or traditional statistical methods would simply miss. It transforms what was once a highly specialized, labor-intensive form of cryptanalysis into an incredibly efficient and often automated process, almost like equipping an attacker with a super-powered, hyper-perceptive ear.
And the impact is just devastating.
Absolutely. The devastating impact is clear. A successful attack used to require millions of traces to recover a key, which at least gave systems a fighting chance. With DNNs, this can be reduced to fewer than 10 traces in some cases. This is what we call an M-trace attack, where an attacker uses just a few traces and a majority voting scheme to quickly recover a key.
Fewer than 10 traces.
Yeah. Theoretically, given the speeds of modern processing, this could happen in microseconds, less time than it takes to blink, a timescale that's almost incomprehensible for security.
That's terrifying, especially for IoT.
Precisely. This rapid attack capability is particularly devastating for IoT devices and smart cards. These devices often operate in untrusted environments, from the simple temperature sensor in your smart home to the payment chip in your credit card or the authentication chip in your passport. They need to perform their cryptographic functions securely for only brief periods, perhaps just long enough to process one transaction, send one data packet, or confirm one authentication. They simply don't have the luxury of performing millions of cryptographic operations before an attacker, armed with a pre-trained ML model, can gather enough traces to compromise them.
So every short transaction is a potential leak point.
Exactly. This makes the threat of ML-powered side-channel attacks incredibly critical and urgent for the pervasive, low-powered digital world we inhabit, where every short-lived transaction could potentially reveal a secret.
Given how potent these side-channel attacks have become, especially with the advent of machine learning, you might naturally wonder what has been done historically to counter them. Researchers quickly recognized the problem in the early 2000s.
Yeah, it's not a brand new problem, but the ML angle really upped the stakes.
Totally. And they started devising countermeasures, evolving their approaches as the attacks themselves grew more sophisticated. One of the earliest and most direct attempts involved switch capacitor, SC-based countermeasures. These were first proposed by Tokunaga and Blau back in 2009, and they demonstrated a significant improvement. Pushing the minimum traces to disclosure, MTD, that's the number of traces needed for a successful attack, to over 10 million.
Which was a big deal back then.
Yeah, it significantly increased the effort an attacker would need.
However, a key limitation here, and a crucial point for modern chip design, was the need for a separate analog bias to clear residue from the capacitors. While effective, this requirement made these designs less scalable across different technology nodes in chip manufacturing. Modern chip fabrication is overwhelmingly digital, relying on automated design flows.
Right, adding analog stuff complicates things.
It really does. Introducing significant analog components complicates verification, increases costs, and limits the ability to simply drop these designs into new, smaller process technologies. Frankly, they were much more analog-like in nature, which complicates integration into modern, predominantly digital chip designs, making them less practical for widespread adoption.
Okay, so the analog part was a hurdle. What else did they try?
Well, other techniques tried to play with the timing of the signals, attempting to obscure the correlations. There was time domain shifting or wrapping, where operations were slightly delayed or sped up.
Think of it like trying to throw off a listener by slightly delaying or speeding up individual notes in a piece of music, but in a predetermined, deterministic way.
Right, trying to misalign the valuable information in the power traces.
For a while, this was a clever trick, trying to misalign the valuable information in the power traces to prevent an attacker from reliably correlating specific power fluctuations with specific cryptographic operations. But the limitation quickly became apparent. These methods were rendered ineffective against CNN-based SCAs.
We touched on this earlier. Convolutional neural networks are incredibly adept at identifying patterns, even when they're slightly shifted or distorted in time.
So the CNNs just saw through the shifts.
Pretty much.
Hmm.
While a simple deterministic shift might have confused earlier, less sophisticated statistical attacks like CPA, CNNs are inherently robust to such transformations. Their convolutional layers are specifically designed to identify patterns regardless of minor shifts in their position within the input data. Think of it like this. If you slightly move a cat in a picture, a well-trained CNN will still recognize it as a cat. Similarly, if the pattern of leaked information was consistently shifted by X nanoseconds, the CNN would simply learn to recognize that shifted pattern.
So it just learned the shifted pattern instead.
Exactly. It just required a slightly more complex internal mapping for the neural network, but it didn't fundamentally obscure the information. The underlying repeating fingerprint was still there, just in a slightly different temporal location that the CNN could easily account for.
Okay. What about changing the frequency?
Similarly, frequency scaling, where the operating frequency of the chip was altered to mask patterns, also had its weaknesses. Attackers found ways to realign the patterns in the time domain by detecting the frequency shift, or simply shifted their analysis to the frequency domain to compensate.
So the attackers adapted again.
They did. It highlighted the challenge of trying to hide information by simple, consistent manipulation rather than fundamentally altering its presentation in an unpredictable manner. The AI, in essence, learned the trick and adapted its observation method.
Were there more recent attempts?
Sure. More recently, other approaches have emerged. Series low dropout regulator, LDO-based, and impedance variation regulator, IVR-based countermeasures showed moderate defense against some traditional attacks like correlational power analysis, CPA, or correlational electromagnetic analysis, CEMA, providing up to 10 million MTD. However, a significant gap, and this is truly critical, was that these techniques were not evaluated against machine learning side-channel attacks.
So they might work against older attacks, but the ML ones, unknown.
Exactly. This is a crucial distinction, as ML-based attacks are a different beast entirely, capable of finding far more complex nonlinear correlations than traditional statistical methods. Therefore, while they might have defended against older attacks, their effectiveness against the modern AI adversary remained unknown and largely presumed insufficient.
Okay, but were there any techniques that did show promise against ML?
Yes, some have shown protection against deep learning SCAs. These include methods like current domain signature attenuation, CDSA, additive masking solutions, and randomized LDOs combined with arithmetic countermeasures. There was also previous work by Ghosh et al., who explored digital signature attenuation, which offered its own set of benefits in reducing the signal-to-noise ratio of leakage. However, even with these advances, The specific challenge of deep learning-based side-channel attacks, particularly those utilizing CNNs, remained a significant hurdle for many existing hardware countermeasures. The attackers, powered by AI and its ability to learn subtle, distorted patterns, were constantly finding new ways to see through the current defenses. This is the precise gap, this critical need for a defense against AI's unique pattern recognition capabilities, that the new research, with its focus on time variance, aims to bridge.
So we've outlined a pretty compelling picture of just how sophisticated and relentless these machine learning-powered attacks have become, and how previous defenses, while clever for their time, have often struggled to keep pace.
A problem really evolved, yeah.
So the natural, urgent question becomes, what do we do about it? How do we build a truly robust defense against an adversary powered by increasingly intelligent AI? And this is precisely where the SCTVTF breakthrough comes into play. The team behind this research had to fundamentally rethink the problem. Instead of simply trying to mask or attenuate the signal, they asked, what if we could make it so inherently unpredictable, so dynamically chaotic, that even the most powerful AI couldn't possibly make sense of it?
That's the core idea.
The core innovation here is the time-varying transfer function, or TVTF. Instead of just making the safe crackers breathing softer or trying to muffle the clicks, imagine the safe itself is constantly shifting its internal components in a completely random way. This makes the clicks come from completely unpredictable places at unpredictable times, making it impossible to learn a consistent pattern no matter how sophisticated your listening device is.
Exactly. The central idea is to dynamically change the transfer function between the local AES power supply and the observable power supply, and they do this using clever, rapidly switching capacitors.
So they're deliberately destroying the temporal correlation that ML models thrive on.
Precisely. And this is a significant advancement because it makes the switched capacitor countermeasure completely digital friendly.
Ah, the digital-friendly aspect again. Remind us why that's so important.
Right. To truly appreciate the elegance here, consider what synthesizable means in the world of chip design. It's far more than just automation. It means you can describe the desired functionality in a high-level hardware description language, like Verilog or VHDL. Specialized software tools, known as synthesis tools, then take this abstract description and automatically translate it into a physical netlist, essentially a blueprint of standard logic gates and their interconnections.
So it fits right into the standard chip design process?
Exactly. This allows for rapid iteration, dramatically reduces human error, and is the backbone of scaling designs to billions of transistors. The fact that SETVTF is fully synthesizable means it can be readily adopted by chip manufacturers without needing complex, bespoke analog design flows. Those flows that often complicate verification, increase costs, and limit scalability across different fabrication processes. It integrates seamlessly into the modern, predominantly digital chip design ecosystem.
Using standard parts.
Yes, by leveraging standard DCK cells for capacitors and power gates for the switches rather than custom analog components.
That's a crucial point for real-world application and scalability. Now let's delve into how this SCTVTF system actually works by looking at its architecture. Okay, so this bucket brigade analogy paints a vivid picture of how the power source is constantly shuffled. It helps us visualize the why. Now, to ground this in the actual hardware, how did the researchers translate this brilliant concept into a tangible physical architecture? What are the specific components that bring this digital dance of randomness to life?
That's an excellent question because the genius is in the implementation. Imagine those buckets are, in fact, precisely engineered switched capacitors. The full SCTVTF architecture is built around a bank of these, specifically N of them, where N in their prototype was 16 individual unit switched capacitors.
16 capacitors, okay. Are they large?
Each one is quite small, actually, around 20 picofarads, so collectively they form about 320 picofarads of on-chip capacitance. These aren't just passive components, they're dynamically controlled by a lightweight SCTVTF controller.
And this controller manages the switching.
Yes. So let's walk through that dynamic process. Discharge, store, charge, store. At any given moment, the controller randomly chooses one capacitor from the bank to actively supply power to the cryptographic core, in their case, a parallel AES 256 engine. We call this the discharge state.
Okay, one discharges.
Simultaneously, another capacitor is randomly selected to be recharged from the main external power supply. This is the charge state. The remaining N2, or 14 capacitors, are simply in a store state, holding their accumulated charge, acting as a buffer or reservoir.
So discharge, charge, and the rest wait.
Exactly. This intelligent, constantly shifting sequence ensures that power is always available to the crypto core, but its instantaneous source is constantly and unpredictably changing, effectively scrambling the power delivery path at every moment. It's like having 16 different little batteries that are randomly swapped in and out to power the device.
That continuous randomized switching is fascinating. But what truly makes it unpredictable, rather than just a complex repeating pattern that an AI could eventually learn? What's the secret sauce for that crucial randomness?
The key to this unpredictability, this digital dance of randomness, lies in sophisticated randomization techniques that are extremely hard for an attacker to predict. The system primarily uses nested linear feedback shift registers, or LFSRs, to generate pseudo-random sequences.
LFSRs, remind me how those work.
Sure. For those of our listeners who might be familiar with basic digital logic, linear feedback shift registers are clever digital circuits. They work by taking a sequence of bits, performing an XOR operation on some of those bits, and feeding the result back into the input, then shifting the entire sequence. This generates a pseudo-random stream of bits.
Okay, pseudo-random.
Now, nested LFSRs take this a step further. We're talking about multiple such registers working in conjunction where the output of one might seed or control another. This nesting dramatically increases the periodicity, meaning the length of the sequence before it repeats itself. Instead of a simple, relatively short loop, you get an extremely long, complex cycle, making the generated patterns incredibly hard to predict or reverse engineer over time for an attacker trying to model the system.
So nesting makes the pattern really, really long and hard to guess.
Exactly. Furthermore, to truly fortify this randomness against any theoretical attacks, for example, if an attacker could somehow reverse engineer the LFSR state, they propose seeding these LFSRs with external true random number generators, or TRNGs.
TRNGs. True randomness. How does that help?
TRNGs derive their randomness from physical, unpredictable phenomena like thermal noise. This seeding provides an uncrackable starting point, further preventing an attacker from theoretically reverse engineering the pseudo-random sequence and thereby predicting the capacitor switching pattern. It's like having a truly random initial shuffle for your deck of cards.
Got it. So nested LFSRs for complexity, TRNGs for a truly random start. Anything else adding randomness?
Yes, actually. What's also fascinating is that even unintentional variations that occur during the chip manufacturing process, known as intra-chip process variations, things like slight differences in the actual capacitance values or transistor characteristics between the individual switched capacitors, actually contribute to the randomness.
So the tiny imperfections in manufacturing actually help.
They do. These subtle physical differences provide an extra inherent layer of physical obfuscation. Even if an attacker knew the ideal design, the real-world manufacturing imperfections would add another layer of unique unpredictability for each individual chip, further complicating any attempt to predict the system's behavior.
So the system leverages not just designed in randomness, but even the inherent physical noise of manufacturing. Now let's look at the brain behind this sophisticated operation, the SC-TVTF controller.
Right, the controller manages this whole dance.
This controller, which is also fully synthesizable as we discussed, uses both 4-bit and 16-bit Fibonacci LFSRs for generating its random sequences. It also incorporates two 8x4 memories and two decoders to manage the switching of these 16 capacitors. So how does this actually play out in real time? Could you walk us through a quick example of its internal logic?
Certainly. Let's take an example shown in their timing diagram to illustrate the process. At any given clock cycle, a random address, say 4, is selected by the LFSRs. This address then points to specific tags stored in one of the controller's memories, for instance, tag 7 and 12.
Okay, so the random address picks specific capacitors via tags.
Correct. These tags correspond to specific physical capacitors that are then chosen for their respective roles, one for charging, one for discharging to the AES core. Crucially, once those capacitors are selected and their tags are used, their tags are immediately swapped to an alternate memory bank.
Swapping banks. Why?
This ensures continuous dynamic operation without any performance hit to the cryptographic core, as long as the TVTF operating frequency is kept high enough to keep ahead of the AES core's demands. It's a beautifully orchestrated high-speed ballet of power delivery and random selection designed to be utterly opaque to an observer.
The magic here is truly transformative. This system effectively shuffles the power traces in the time domain. When an oscilloscope captures the power consumption, each tiny time sample it records acts as a feature for an attacking deep neural network. But with SC-TVTF, Each of these samples is now randomly scrambled and reordered in time relative to the actual cryptographic operation. It's not just a subtle shift. It's a complete, unpredictable rearrangement.
This means the feature set presented to the DNN during an attack phase becomes fundamentally different, cycle by cycle, from what it was trained on.
It breaks the learning process for the AI.
Exactly. It's like trying to use a fingerprint database where all the fingerprints are constantly changing shape and position, making consistent identification virtually impossible. The inherent time variance completely disrupts the temporal patterns that ML models rely on to identify specific operations or data values. The AI simply cannot find a stable, repeating pattern to learn from, rendering its sophisticated pattern matching capabilities utterly useless. The information is there, but its temporal context is destroyed beyond recognition by the attacker's model.
Of course, the real test of any groundbreaking technology is in its performance, particularly against the formidable threats we've discussed. This team didn't just theorize, they built and tested.
Right, they put silicon where their mouth is, so to speak.
Exactly. They created the first 65mm TSMC CMOS integrated circuit, or IC, that demonstrates this specific time domain MLSCA resilient technique. It's a tangible piece of hardware proving the concept in a real-world fabrication process. The chip includes a parallel AES-256 implementation with a 128-bit data path, all within an active area of just 0.15 millimeter itself. And it's important to emphasize that their primary goal here was to test the time domain obfuscation itself. So they intentionally used a standard lookup table, LUT-based SBox, the SBox being a crucial nonlinear component in AES where a lot of leakage often occurs.
That's a good point. Using a standard SBox isolates the effect of SCTVTF itself.
Precisely. This choice allowed them to isolate and precisely measure the effectiveness of the SCTVTF countermeasure without confounding factors from other arithmetic countermeasures, giving a clear picture of its standalone power.
Okay, so let's get into the numbers. What were the operational details?
Well, digging into the operational details, the AES-256 core was operated at 10 MHz with a 0.8V VDD, pretty typical operating parameters for such embedded systems.
Okay, and the power consumption?
In its unprotected mode, the AES consumed 189 microwatts of power. In the protected mode, with the SCTVTF countermeasure enabled, power consumption increased to 248 microwatts.
So there's an overhead, but how much? And what about area?
Now let's talk about the physical footprint. The added countermeasure active area is only 0.03 millimeter for test. This translates to a lowest-to-date overhead of just 20% in area and 25% in power for the entire system relative to the unprotected AES core.
Wow, 20% area, 25% power. That's incredibly efficient, especially when you consider the dramatic level of security it provides against advanced attacks. That's really quite low overhead.
It really is.
Yeah.
It's worth noting that previous work by Ghosh et al. Explored similar techniques in conjunction with digital signature attenuation, but this is the first time SCTVTF has been rigorously tested as a standalone countermeasure, specifically against ML-based side-channel attacks, providing a clear benchmark of its unique contribution.
Good to clarify. So how did they actually try to attack this thing? What was the setup?
To truly understand the SCTVTS effectiveness, the researchers set up a rigorous attack methodology designed to push the limits of modern ML-based side-channel analysis. They targeted the first key byte of the AES-256 encryption, a common approach for breaking cryptographic keys sequentially. During the training and profiling phase, a fixed plaintext was repeatedly fed to the AES-256. They then captured power traces for all 256 possible combinations of that first key byte using a high-speed 5 gigasamples per second oscilloscope.
5 gigasamples. Capturing a lot of detail there.
Oh yeah. This allowed them to capture incredibly granular detail of the chip's power fluctuations. These thousands of captured traces were then fed to the deep neural networks for training, teaching the AI to associate specific power patterns with specific intermediate values and ultimately specific key byte hypotheses.
So they trained the AI attacker really well.
Exactly. Once the DNN models were meticulously trained and optimized to be as effective as possible, meaning the attacker's tools were at their absolute peak performance, the testing or attack phase began. The trained DNN was then unleashed to recover the first correct key byte from a target device, the AES-256 core, under attack, using only its leaked power traces.
And they used standard ML models for this.
They employed two primary DNN architectures for their attacks: full convolutional networks, or FCNs, and the more widely known convolutional neural networks, or CNNs, both known for their robust pattern recognition capabilities. They also went through an extensive process of hyperparameter tuning, which is essentially optimizing the DNNs to make them as effective as possible for the attack.
Right, tuning the AI itself.
Yeah, they noted that deep models, if not carefully tuned, can actually overfit when dealing with one-dimensional data like power traces. This means the model learns the training data too well, including the noise, and performs poorly on new, unseen data.
A common problem in ML?
To counteract this and ensure the attacker's model was truly robust, they used adaptive learning rates and meticulously identified optimal neuron counts within their network layers, such as 560 neurons in certain layers. This rigorous approach ensured that the impressive results of SCTVTF aren't due to a weak attacker, but rather a robust defense against highly optimized, state-of-the-art ML tools. Now, for the moment of truth, the stunning results that truly redefine what's possible in hardware security. Let's start with the unprotected AES-256. After all that meticulous setup and rigorous testing, what were the real-world performance gains in terms of traces needed to break this system?
Okay, let's hear the baseline first. How did the unprotected chip fare?
The results, frankly, redefined what we thought was possible in hardware countermeasures. For an unprotected AES-256 system, optimized FCN and CNN models could be trained with 200,000 traces to achieve 87% accuracy in identifying the correct key byte.
200K traces for training. Okay. But how many to actually attack it successfully?
But here's the critical part. Only 5,000 traces were sufficient to recover the correct key with high confidence using an M-trace attack, leveraging the concept of majority voting across those few traces.
5,000. That's not many at all in the grand scheme of things.
It gets worse. In some scenarios, they found success with as few as 5 traces.
5. Just 5 power traces.
5. Think about that. Thousands of traces for training, then just a few more, and your secret is gone. For an IoT device operating for mere seconds or performing a single transaction, this represents an almost instantaneous compromise.
It truly paints a chilling picture of just how vulnerable a device performing a single quick transaction could be in an untrusted environment. That's the sheer devastating power of these ML attacks.
5,000 traces, or even just 5. That's terrifyingly fast. It renders many conventional security assumptions completely moot for these short-lived transactions. So what happened when SCTVTF was enabled? Did it provide a meaningful defense against this level of AI-driven attack?
Okay, the moment of truth. How did SCTVTF stand up?
Meaningful is an understatement. When the SCTVTF countermeasure was active, the same highly optimized FCN and CNN models could not be trained to detect the correct key even after collecting 500 million. That's 500 million traces.
Wait, 500 million traces and still nothing?
Still nothing. Think about that number again. From needing mere thousands of traces to compromise a system to literally 500 million with the countermeasure active and still no success.
That's just astronomical.
Even when the researchers went to extreme lengths, averaging 1 million traces 100 times to reduce measurement noise, the attack still failed. The AI simply could not find any consistent, discernible pattern in the dynamically randomized power traces to learn from.
500 million. You're telling me we went from needing mere thousands of traces to compromise a system to literally 500 million with the countermeasure active and still no success? That's an astronomical, almost incomprehensible difference.
Right. What would it even take for an attacker to collect 500 million traces? We're talking about an immense amount of time, computational resources, and data storage just to attempt an attack, let alone succeed.
This demonstrates a truly profound disruption of the attacker's ability to learn any meaningful patterns.
And how does it compare to other defenses?
The comparison with previous state-of-the-art really highlights this. This design achieves an improvement of greater than 100,000 times in the number of traces needed to train an attack compared to an unprotected AES system.
100,000x better than nothing.
And even when compared to the best existing state-of-the-art solutions, it shows more than a 5x improvement.
So 5x better than the previous best. That's still huge.
Absolutely. This isn't just a step forward, it's a giant leap in securing these critical devices against the most advanced forms of side-channel attack that AI can muster.
So the results are clearly impressive. What about the broader impact? Does this only work for AES?
That's a great question. And one of the most powerful implications of this research, beyond the impressive numbers and the innovative technical solution, is that the proposed SCTVTF countermeasure is fundamentally generic.
Generic, meaning?
Meaning it's not tied to a specific cryptographic algorithm or a particular hardware implementation. What this means is that it can be seamlessly integrated and used with any cryptographic core, offering a broad, foundational layer of security regardless of the underlying encryption scheme. This is incredibly valuable in a rapidly evolving threat landscape.
And this genericity couldn't come at a more crucial time. You, our listener, might be aware that NIST, the National Institute of Standards and Technology, has been hard at work selecting new standards for the next generation of cryptography.
Yeah, the post-quantum crypto efforts and lightweight crypto.
Exactly. This includes new standards for post-quantum public key cryptography, like Kyber for public key encryption and dilithium for signature schemes, specifically designed to withstand attacks from future incredibly powerful quantum computers. They've also selected new standards for lightweight cryptography, LWC, such as ASCON, which is vital for those resource-constrained IoT devices and smart cards we've been discussing, devices that simply can't afford heavy cryptographic overhead.
Right, and SCTVTF fits right in. Consider Kyber, for example, which in some implementations uses AES as a pseudo-random number generator within its algorithms. This generic SCTVTF countermeasure can not only be used to protect the AES component within Kyber, ensuring the integrity of those pseudo-random numbers,
Okay, protect the AES part within Kyber.
but theoretically, its underlying principle of time-varying obfuscation could also be adapted for Kyber in general, or indeed any of these new cryptographic primitives. This means it's incredibly future-proof, relevant, and applicable for both current cryptographic standards, like AES, and the emerging next-generation standards. Standards designed to protect us for decades to come, even against the threat of quantum computing. It's a versatile shield for the future of digital security, capable of adapting to new algorithms and new threats.
So for you, the listener, what does this all mean for your everyday life? It means the tiny, powerful computers in your smart devices, your health trackers, your car keys, your smart cards, your passport chips, all the ones that handle your most personal and sensitive data, could soon be dramatically more secure against these incredibly sophisticated, AI-driven, eavesdropping attacks.
It really is a crucial step.
Yeah, a crucial step in ensuring that the physical world, the subtle electrical signals and electromagnetic whispers of a chip, doesn't betray the mathematical security of our digital lives, safeguarding our privacy and data integrity in an increasingly connected world. What a journey we've been on today. We started by understanding the insidious and evolving threat of ML-powered side-channel attacks on our ubiquitous IoT and smart devices.
And how fast they can be. Microseconds.
Exactly how these attacks can strip away cryptographic secrets with alarming speed, sometimes in mere microseconds. We then explored the ingenious SCTVTF countermeasure, a groundbreaking technique that uses random time variance in power delivery to utterly foil these advanced AI-driven cyber sleuths.
Making the physical features totally meaningless to the AI.
Right. We saw how it makes the physical features of power consumption meaningless to a trained neural network, effectively scrambling the attack surface and making any learned patterns irrelevant. And the numbers truly speak for themselves. Over 100,000x improvement in traces needed to train an attack compared to unprotected systems.
And over 5x against the previous state-of-the-art.
And more than a 5x improvement against the previous state-of-the-art solutions, all achieved with minimal hardware overhead. This is a monumental step forward in hardware security, changing the economics of side-channel attacks by making them practically infeasible.
It really is. And this deep dive into SCTVTF highlights how the battle for digital security isn't just in the algorithms or the code, but in the very physics of how our hardware operates. It raises an important question. As AI continues to advance, constantly seeking patterns and correlations in the world around us, will future hardware security be less about making signals silent or hidden?
And more about making them chaotic.
Exactly. More about making them utterly chaotic, meaningless, and fundamentally unpredictable to any observing intelligence. It shifts the paradigm from concealment to confusion.
Something profound to ponder as you look at all the connected devices around you, silently performing their digital work. Stay curious, stay informed, and we'll see you next time on The Deep Dive.